Hello, calculus students! We're continuing our lessons in the learning target limits and asymptotes. Our previous lesson was connecting infinite limits and vertical asymptotes, and our current lesson that we'll learn about right now is connecting limits at infinity and horizontal asymptotes. So we're going to start off with a warm-up per usual. Go ahead, take your time to write this in your notebook in about 5 minutes to solve it out, then come back and check with me. Welcome back! Here is what I got for the warm-up. So I was supposed to find the vertical asymptotes, so I took the denominator and I set the denominator equal to 0, and the value of x that makes the denominator 0 is -2. So x equals -2 is a vertical asymptote. And then I checked the behavior to the left and to the right of the asymptote. And when I did that, I got negative infinity as x approaches -2 from the left. And I got positive infinity as x approaches -2 from the right. I think one thing to watch out, a common mistake here is what to put for the numbers to the left and to the right of a negative number. And so a bigger negative number is to the left, so -2.1 is to the left of -2 on the number line, and a smaller number, -1.9, is to the right of -2 on a number line. So that was a little bit tricky there. And then this is just kind of something like what our graph will look like, at least at -2. I don't really know what else is happening here, but at -2, I know that that's where the function is going to the left and to the right. Okay. So previously we learned about infinite limits, and infinite limits are when a limit is approaching infinity. Now we're learning about a limit at infinity, and this is when the value of x is approaching infinity. So here's the formal definition. When the limit as x approaches infinity of f of x equals b, or the limit as x approaches negative infinity, so infinity and negative infinity are both infinite numbers, equals b, then y equals b is a horizontal asymptote. Okay, so basically a horizontal asymptote is what happens when your values of x get really, really big or really, really big in the negative direction. So, for instance, this is heading towards positive infinity and this is heading towards negative infinity. And so, as you go towards those two limits, if the limit is tending towards a number, b, that will be your horizontal asymptote. Okay, so I want to relate this to what we already know about horizontal asymptotes. So these are the 3 rules that we learned about horizontal asymptotes in the beginning of the year: top heavy, bottom heavy, or balanced. And back then I used this language. What happens when x gets really big? And so we are thinking about when x gets really big, what would happen to the number? Now that we know about limits, we can describe that. Instead of saying what happens when x gets really big, we'll say what is the limit as x approaches positive or negative infinity. And so all these cases, which is how we would have written them before, now I might say, okay, what's happening to the limit as x approaches infinity of this function f of x? When it's top heavy, the numerator is going to grow a lot faster than the denominator, so that will go off to positive infinity, which means there's no asymptote because it's not going towards a number. When the function is bottom heavy, if I take the limit as x approaches infinity of f of x, the denominator will grow a lot quicker than the numerator. When that happens, it becomes a very small number. So the limit is 0, which means there's a horizontal asymptote at 0. Okay? And then finally, in a balanced equation, if I were to take the limit as x approaches infinity of this equation, you can see that they circled that there were the leading terms. And we look at the coefficients of the leading terms because they balance each other out. They have equal power in the numerator and denominator. We just take the fraction like that. So there's a horizontal asymptote at 2 in this case. And just a reminder, horizontal asymptotes are always y equals. Since it's a horizontal line, that is going through a y value. So it's y equals, whereas a vertical asymptote is x equals. Example 1 might feel a little bit like review because we are using the rules of horizontal asymptotes to find horizontal asymptotes, but the directions say to specifically use limits at infinity. So we're going to bring the idea of limits at infinity to identify the horizontal asymptotes. Cool. So I'm going to take the limit as x approaches infinity of f of x. Whenever I'm looking at infinity, I want to observe the leading coefficients. I guess infinity. So I'm just looking at the leading coefficients and I see that this is balanced. So when it's balanced, I was looking at the leading terms and I see it's balanced because they are both raised to the second power. And so I'll look at the leading coefficients, which are 1 and -4. So that is my limit. And so since the limit as x approaches infinity of f of x equals -1/4, then f of x has a horizontal asymptote at y equals -1/4. And so in the future or on your AP exam, when you are asked to find a horizontal asymptote, this is the way you will prove that something is a horizontal asymptote. You will take the limit as x approaches infinity and use this definition right here. Okay, so in the future for the AP exam, this is how you're going to prove the value of a horizontal asymptote by taking the limit at infinity. Cool. So let's do this for the next one. So I'm finding the limit as x approaches infinity of g of x. Here, it's a little bit more challenging to find the leading coefficients because things are being multiplied together or squared like that. And so I'm just going to figure out in the numerator what is my leading coefficient, in the denominator what's my leading coefficient. So I see that when I multiply 3x and -4x together, that is going to give me the highest power. So when I multiply those together, I get -12x squared. And then the biggest power in the denominator is this 2x, but I've got to square it, and so that is 4x squared. I want to make sure these things are not equal to each other. I'm definitely not saying that they're equal to each other. Right here, I'm just trying to identify the leading terms in the numerator and denominator. So if you need that little reminder, these are just the leading terms. Okay, I just found them in both the numerator and denominator. Anyway, I have another balanced equation. So they both have a power of 2, which means I'll look at the coefficients, which are -12 and 4, which is -3. So I can say g of x has a horizontal asymptote at y equals -3. Cool. J of x. This equation looks really simple, but I want you to look at it real quick and try to figure out if this is top heavy, bottom heavy, or balanced. Some of you might be struggling a little bit right now. So I want to give you a little bit of vocabulary. This is a power function. where it's just x raised to a power, and this is an exponential function. Okay, so power function could be like x squared, x cubed, x to the fourth, where x is the base and then it's raised to a power. An exponential function is different because x is the exponent. And I want you to try to guess, using your knowledge, which one of these is going to get bigger. What do you think? It's an exponential. We know when you're in Algebra 1, you talk about like bunnies having bunny babies or zombies in the zombie apocalypse, and you learn that exponential functions go really, really fast. So because x is in the exponent in that problem right there, that denominator is growing faster. So this is bottom heavy, okay? Exponential functions. I'm gonna add grows fastest. So this grows the fastest. So this is a bottom heavy. If you need all these notes, just write it down so you know. So thus, when I take the limit as x approaches infinity of j of x, it's a bottom heavy function, which means the denominator is getting really big. This function is going to 0. Cool. Oh, so I gotta say the horizontal asymptote. So j of x has a horizontal asymptote at x equals 0. Cool. And then D, I just wanted to give you a little bit more experience with the exponential functions, so you can kind of get used to them. This has an exponential function both in the numerator and the denominator. So I want you to guess, is this top heavy, bottom heavy, or balanced? This is balanced because the exponents here, the exponents are the same. So in order to determine whether it's top heavy, bottom heavy, or balanced, you really have to look at those exponents and figure out which one is bigger. In this case, they're the same, so I have to look at my coefficients. So the limit as x approaches infinity of f of x will be the numerator's coefficient over the denominator's lead coefficient. Okay, and so f of x has a horizontal asymptote at y equals -2/5. Gorgeous. Okay, so these are how to use limits at infinity to find horizontal asymptotes. The next examples, so example 2 and 3, are strictly using the definitions, but they include rules for vertical asymptotes and horizontal asymptotes. So we have both infinite limits and limits at infinity in these next two examples. Review. Okay, so the continuous function f is positive and has a domain of x greater than 0. Okay, so the domain is 0 to infinity. I like rewriting the domain like that. If the asymptotes of the graph of f are x equals 1 and y equals -3, which of the following statements must be true? Pardon me. So I'm gonna kind of break these up. I have two asymptotes. I have x equals 1. This is a vertical asymptote. And then I have, y equals -3. This is a horizontal asymptote. So I want to just focus on my definitions without really looking at those options, because I feel like the options over there, A, B, C, and D, are kind of like, they're kind of hard to look at. So I want to figure this out separately. So flashback to my vertical asymptote infinite limits definition. Do you remember it? Right here. So in order for A to be a vertical asymptote, then the limit as x approaches A goes to positive or negative infinity. So I know that I have to have, oops, something like that, something like this. Right? It's got to be something like that. And then my other option, oh, for horizontal asymptotes. So now I'm going to use my limits at infinity, which I just learned here. So when x is approaching infinity equals b, y equals b will be a horizontal asymptote. So I'm going to use that same definition here. So when the limit as x approaches infinity of f of x, and I know that it has to be x is going to positive infinity, not negative infinity, because of my domain. It doesn't go to negative infinity. And that equals -3. That will cause a horizontal asymptote. So now I'll look at which ones match this, and it's this one down here. This one's a little different because it adds 1 to the right. Remember, it doesn't really matter if we're looking from the left or the right, as long as you're approaching from one of the directions towards that value of 1 and it goes to infinity, there will be a horizontal asymptote there. There will be a vertical asymptote there. Okay. Cool. And then example 3. If the graph of y equals ax plus b over x plus c, so they're just giving me this weird equation with lots of variables that I don't know in it. Has a horizontal asymptote at y equals -1 and a vertical asymptote at x equals 5. What is a plus c? Okay. So I need to figure out these two values. I need to know a and c. I don't really care about x and b, apparently. I just need to know what is a plus c. So, a horizontal asymptote right here at y equals -1, if I get a value other than 0, I know that this is a balanced equation because I have to take the coefficients between the top and the bottom. So, if the coefficients equals -1, I know that I have coefficients that are -1 over 1, right? So this is like -1 over 1. So I'm going to say a is -1, like that. And so then, when I look at my leading terms, it's -1 over 1, which gives me that horizontal asymptote. Perfect. Cool. And then, if I have a vertical asymptote of x equals 5, I know that 5 is the x value that will make the denominator 0. So I know that there's something that looks like this. In the denominator. So if x minus 5 is in the denominator, when you plug in 5 for x, it equals 0. So I need that to be in the denominator, which gets me here, -1x plus b over x minus 5. So there it is. That will give me my vertical asymptote. So let's answer the question. This is how the AP exam can be kind of tricky. It asks, okay, what is a plus c? So we did all this beautiful work to find out what they are. Don't forget to actually answer what the question is. So I know that a equals -1 and c equals -5 because of that negative sign right there. So a plus c equals -1 plus -5, which is -6. There's my final answer. Cool. So example 1 was straight up just how to use that definition of limits at infinity to find horizontal asymptotes. And examples 2 and 3 combined all your knowledge about vertical and horizontal asymptotes and how they relate to limits to solve these two problems.